Okay, we're going to continue on here with kinetics. Hopefully wrap it up our chapter that we've been talking about. So last time we talked about several things. We talked about again how to calculate the orders. And as we talked about in lab as well, we use this equation here typically. And remember that this usually accompanies a table of values, kind of like what you're going to create in lab in that experiment, where you have multiple molarities or concentration of reactants. You also have sort of the initial rates there. And remember that when you go to that table, you want to choose two entries where really you keep one of the reactants constant and the other one varies. So you have just one unknown. And again, that allows you to solve for the orders. Remember that you have to do that first to get the completed rate law. Once you get the completed rate law, you then could use it and the same table to figure out what the value of the actual rate constant is. And again, you could go into any of the experiments in those tables. Once you have the orders, you can plug all the numbers in. Thank you. And you can solve for the value of the rate constant. We then got into really specific orders of reactions or overall orders of reactions. There's first order. There's second order. And there's zero order reactions. And remember that each of these really have a specific sort of graph that goes with it. And they also have a specific type of units that we associate with the rate constant. And that's really important when we think about these guys. The K units here for first order is typically reciprocal seconds, or 1 over some unit of time. For our second order, it is 1 over molar seconds, or again, any type of unit of time. For our zero order, it is molarity over seconds. And the importance of that, again, is that they will not always, in a problem, tell you straight out what order you're dealing with. Is it first order, second order, zero order? But they will give you the value of the rate constant and the units associated with it. And again, they just expect you to sort of know, based on those units that you see, what order of reaction you're dealing with. And there was a lot of concentration time sort of integrated rate laws for these guys. For first order, it's the natural log of A equals the natural log of A naught minus KT, where A is sort of the final concentration, A naught is the initial concentration. For second order, it's 1 over the final concentration equals 1 over the initial concentration plus a KT. And for zero order, it is the final concentration equals the initial concentration minus KT. Now, each of these also have a specific half-life equation. Thank you. That goes with them. And remember that the half-life basically is the time it takes for half of whatever you started with to basically go away. So for our first order, it's the natural log of 2 over the rate constant. For our second order, it is 1 over K times the initial concentration on the bottom there. So for second order, the initial concentration does play a role in the half-life of that equation. And so does it for the zero order, which is the initial concentration divided by 2K. So both the second and zero order half-life is dependent on the concentration, the initial concentration. So depending on how large or small it is, you may have actually a greater effect on the half-life. There are some graphs that specifically kind of go with these, and these are typically our straight line graph. That's the natural log of A versus time. Will give you a linear line-ish if I drew it straight. will give you where the slope is equal to minus the rate constant. For our second order, we graph 1 over the concentration versus time. That will give us a linear line where the slope is equal to K. And lastly, for our 0 order, we do concentration versus time, giving us a linear line where the slope is equal to minus K. Remember that we also saw this graph here for first order, but it was not a linear relationship. So again, it was a sort of exponential decreasing with time relationship. Now, after we talked about these, we started to talk about energy of reactions and sort of temperature. And we looked at some energy diagrams. And we had some different energy diagrams. We had one that looked something maybe like this, where that's our reactants, that's our products. And we also had one where looks maybe something like this, reactants and products. And remember that there is a minimum amount of energy required for a reaction to take place, and that is the activation energy. And that is the hill that the reactants has to climb to get to the other side. And for this guy here, this would be the hill. This reaction or energy diagram on the left is a exothermic reaction, as the delta H between these two would be negative, and that would give us an exothermic reaction, as opposed to here where the delta H would end up being a positive value, would be an endothermic process. So as we talked about, remember that not all collisions will lead to actually products being formed. There's really two important things that has to happen in order for a reaction to really take place. And that is there needs to be collision in sort of the correct location, sort of like the active site, if you will. And it needs to have that minimum amount of energy or that activation energy to get up and over that hill. So obviously the bigger the hill the reactants has to climb, there's going to be probably a smaller proportion of molecules that can do that. And thus would mean that the reaction would move slower. And then if you have a larger activation energy, a smaller activation energy, there would be a greater proportion of molecules that could get up and over to the other side, and the reaction would proceed quicker. Now, there is a relationship, which is the Arrhenius relationship of sort of temperature and the rate constant. And really the sort of graphical version, which I think is where we kind of left off, is the natural log of K is equal to minus E of A over R 1 over T plus the natural log of A, I think. Equal to mx plus b. And the typical graph that we do is what it says there, natural log of K, 1 over temperature, and this does need to be in Kelvin. And this typically will give you a linear line where the slope of this line will equal minus E of A over R. R is the gas constant. It is the one that involves energy, 8.314 joules per Kelvin per mole. And remember that this line here is going to be a negative slope. Along with this negative slope, we'll turn our activation into a positive number, which is what it should be, as we can see here, positive sort of number going into that spot. Any questions on any of those things we talked about last time? Okay. So that is sort of where we left off. And this is, again, sort of the natural log version of the Arrhenius equation. This, again, is really the one that we use most of the time if we're doing some type of plotting of this type of nature. We have a bunch of K values, which you would then need to take the natural log of each of them. We also have temperature values, which in a lot of cases you will have to convert to Kelvin. A is the frequency factor, and you can think of it as really the proportion of molecules that have enough energy to get up and over to the other side. I think we talked about at the very end there. Typically, the units of A will actually be the same units that you see for the rate constant. So whatever units go with the rate constant is typically kind of what you see with the A value. And by the way, the A value there is obviously the y-intercept, and that would be where the obviously line crosses the y-axis there. So let's say we had some values like this in a table. And as I mentioned before in this chapter, you may have to make some graphs along the way to answer some homework problems. But we do have the temperature. It is actually in Kelvin, which means we don't have to do that conversion. We do have the K value, which we do need to do conversion. So we do need to convert this really into 1 over the temperature value. We do need to take this guy and take the natural log of K for all of those values. And if you do that and plot it, you will get a graph that looks something like this. If you do your best fit graph like we did before on some of those experiments, and you'll get the equation. So we could use this equation to figure out the activation energy and the frequency factor, which is A. So why don't you take a moment or two using this equation, which is a result of all that data we just saw there. Calculate both the activation energy and the frequency factor here, what it would be. Natural log of K is equal to minus E of A over R, 1 over T plus the natural log of A is equal to Y is equal to MX plus B. So once again, here we will use the slope to allow us to solve for it. And that is this number here. That is the slope. So the slope here would equal minus E of A over R. We do want to take the negative with it since it is a negative slope that's happening here. That gives us negative 1.12 times 10 to the 4 equals minus E of A over 8.314 joules per Kelvin per mole. We're going to multiply the 8.314 to the other side, and not just 8.314. We also want to take the negative over there as well. And that will get us, making sure to use our exponent button, will get us 93116.8. The units here are actually joules as it comes from the R value. Typically, activation energy is given in kilojoules. So maybe we round it off to 93.1 kilojoules would be our activation energy. Once again, it should be a positive number, so it's important to take that negative to the other side as well. Any questions on that part there? Now the questions. Now the frequency factor is the A, and that is equal to the natural log of A. So it's important to know that the natural log of A will equal our y-intercept, and that is our y-intercept in this case. So that would give us the natural log of A is equal to 26.8. To get rid of the natural log, right, we're going to take the E of both sides there. That will cancel those out and just give us A. Now we're not going to do any type of negative or anything like that. We're just going to simply take the E there of the other side. And that will get us an E of, what we got there, 26.8. We'll call it 4.36 times 10 to the 11, it looks like. Now, once again, as we talked about the units here, they do really fall back to the units that we see here for the rate constant, which would be 1 over molar seconds in this case. So it would be 1 over molar seconds would be our units that are associated with that. Again, when you take the natural log of the K, it loses its units, but when you take the E back of it on the calculation, the units come back basically in that case. Any questions on how to graphically solve that? Yeah. It is. So graphically speaking, that is the A in that equation, and that is equivalent in this equation to the y-intercept that you would have. It always is. So it is equivalent to the y-intercept, but remember, it's not what A equals. It's actually the natural log of A equals the y-intercept. So you do have to do that little E calculation, but it always will in this type of graph. Yeah. Other questions? Just like always, the slope here will basically always equal minus E of A over R and stuff. Yeah. Yes. Typically speaking, activation energy is usually given in kilojoules. It doesn't have to be. You could leave it in joules. But just like maybe you're familiar with like delta H is typically given in kilojoules. Unless it's specifically asked for kilojoules. But if it just asks you to calculate the activation energy and didn't not tell you to give it in specific units, then either one is fine. But usually activation energy is in those kilojoules. Yeah. There's 1,000 joules in a kilojoule. So basically divide by 1,000 the joules. Other questions? Yes. No, you're not. It's A is the frequency factor. So it's basically the proportion of units that have a proportion of molecules that have enough energy really to get up and over to the other side. So the typical units of frequency factor, when you solve it from a graph, will usually end up being the same as the rate constant units. And that's really because if you follow this line, right, the y-intercept crosses the y-axis. So basically what you're looking at is the natural log of k. So when we do this E of it, the natural log goes away and it kind of reverts back to the same units at that point. Just like other questions? R is a constant, it's a gas constant. Yeah. Yeah. It is. Oops. Yeah, so this was solving, this is actually solving it. So that negative that you see here is this negative, and that's the R. So that's like the word version of solving for the activation energy. So that's how the negative got over there. But it is a positive number. Yeah. Is there a question? You would in this sort of graph, you would use basically those two numbers if you needed to, the slope and the y-intercept. Other than what we just did, no. Yeah. So obviously on a quiz or exam, I probably want to have you graph it. You may be given the graph and the equation. You know what to do with that equation. But I will say in the book, in homework problem, you may have to lay up some graphs yourself. Yeah. So, and especially in this kinetics chapter, there's a lot of homework problems sometimes that the only way to sort of solve it best would be to make like a quick Excel graph and get the equation and stuff like that. So keep that in mind as you work through the homework problems. If you come across one, like, not really sure if I need to make a graph, you might need to actually make some graphs. Yeah. Other questions? Okay, so this is sort of the graphical version where obviously you had some different rate constants and you have some different temperatures, which we'll get some experience doing in the next experiment that we do. You could graphically determine the activation energy from a graph for a reaction. Now, in all cases, we don't usually want to graph a lot, so there is sort of a more mathematical version of the Arrhenius equation that you could use if you have really two pieces of information, maybe two rate constants, two temperatures. You could sort of graph non-graphically solve for it. So this is sort of, you could think of it as the non-graphical way to solve for activation energy, temperature. You could really solve for anything here, rate constant. And that is the natural log of K2 over K1 is equal to E of A over R, 1 over the temperature, first temperature, minus 1 over the second temperature. These temperatures do need to be again in Kelvin. That again is our gas constant, which is 8.314 joules per Kelvin per mole. And that's obviously our activation energy and our rate constant at two different temperatures. I will say that there is maybe like 3 versions of this formula that you may see around town. Some where they distribute out the minus sign in the parentheses and they combo the denominator. So there are some various versions, and even a version where you'll see like the negative on the outside and stuff like that. So we'll roll with this version. And you could use this really to solve for anything. Like I said, you could use it to solve for a rate constant at a different temperature. You could solve the temperature, you could solve for the activation energy, and stuff like that. So you can really manipulate it to solve for a lot of things. So why don't we try that there? Reaction here has a rate constant of 2.57 at 701 Kelvin and 567 at 895 Kelvin. Find the activation energy in kilojoules per mole. Yes. That's what I said. There's a few different versions of that equation. And in this particular version, it's been distributed inside the parentheses. And another version of this equation is actually still on the outside, but the 1 over T1, all that's different. It's switched around. And there's a version where they combo the inside of that. So in this particular version, it's been kind of distributed in to the parentheses part. Yeah. But don't be surprised, like I said, you can find this version of this equation in a couple of different forms where you will see the negative on the outside and you may not see it. All right, so give it a go here, see what you come up with. We're looking for the activation energy here. All right, let's take a look. So we have obviously a rate constant given to us, which is 2.57. It goes with a temperature of 701. It's already in Kelvin, so we don't have to do any type of conversion, which is good. We got another rate constant there, which is 567. And that's our temperature there of 895 Kelvin, also converted. We're looking for the activation energy here. So we could use our 2-point version. We just saw there, natural log of K2 divided by K1 equals E of A over R, 1 over T1 minus 1 over T2 in this case. At this point, we'll take the natural log of 567 divided by 2.57 equals E of A, 8.314 joules per Kelvin per mole, which is a constant. 1 over our initial temperature there of 701 minus 1 over 895 Kelvin here. At this point, just a reminder, mathematically speaking, you want to divide first and then take the natural log, not the other way around. So we'll do a 567 divided by 2.57. We'll take the natural log of that. Will give us, looks like maybe something like 5.39645 equals E of A over 8.314. I'm going to clean up what's in here. So if I do that, that's 1 divided by 701 minus 1 divided by 895. Gets us 0.000309215. At this point, I need to multiply the 8.314 to the other side. I got to multiply that to the other side and also divide then that guy to the other side, right? So if we do that, we will end up with, you'll find my number, there it is, take that, times 8.314 divided by my 0.0003 number there. Going to get us an E of A after we multiply, then divide of 145096. The units here would be joules, and we'll turn that into kilojoules at 145 in this case. Yeah. Any questions on that calculation there? Yeah. It doesn't, is your question, it doesn't matter which one you call K1 or K2. It really doesn't, as long as you keep the K and the temperatures together. So whichever one you call K1, the appropriate temperature should be temperature 1 and vice versa. So as long as you keep them together, they should work out the same. In general, most people just roll through whichever one comes first. They'll call it the first one and stuff like that. But it really doesn't, as long as you keep those two values together. Other questions on that? Yeah. Technically I didn't. It is, well, the Kelvin would be gone from here. And really the moles would still be there, but I just left kilojoules. So it really is kilojoules per mole at this point would be the units. Yeah. But the Kelvin would go away right about there. Other questions? Okay, let's take a look at another one here. It's often said, if we, as we talked about earlier, if you double the rate reaction will double. If you raise the temperature about 10 degrees Celsius, calculate the activation energy for such a reaction. Here you could use that information to help you do it. Helpful hints, this is really a 10-degree difference in the temperature. Obviously, if you subtract 273 from each of them, it's 27 degrees Celsius and 37 degrees Celsius. So that's the 10-degree Celsius difference. The rate doubles, so that means the rate constant would double between the initial and the final rate constant here. And that really means on the left-hand side here, we basically have the natural log of 2 in that case, as this guy on the bottom would be half the guy on top. So that basically be the natural log of 2 is going to equal our E of A, which is what we're looking for, our 8.314. In this case, they picked these two temperatures, so we'll use them here, 1/300 Kelvin minus 1/310 Kelvin. We'll clean up what's in there, and that would get us 1 divided by 300 minus 1 divided by 310. Going to give us 0.000107527. In this case, we're going to do the same math. We're going to send the 8.314, multiply it to the other side, and then we're actually, again, going to divide that guy back to the other side. And that would give us a natural log of 2, which is 0.693, divided by, or multiplied by 8.314. And then divided by our 0.0000107, going to give us an activation energy here of 53594. Again, the joules will be the units here per mole. Dividing it by 1,000 to put it in the typical units of activation energy gives us something in the ballpark of, we'll call it 53.6 kilojoules would be our activation energy in this case. Any question on that? So this is obviously more of the mathematical approach. If you have some information or 2 points, really, if you have, why they call it the 2-point equation is technically, if you have information about 2 points along that line we looked at, you could just plug and chug into this equation basically and solve for it. Although in these 2 examples here, we solve for activation energy, you could solve for anything in this equation. So you could solve for K values, you could solve for temperature values, you obviously could solve for activation energy. So you could really use this equation to solve for any of those things. In an example where you might have been given the activation energy and 1 rate constant and 2 different temperatures, you could figure out at the second temperature what the rate constant would be and vice versa. Any questions on any of that? So you do need to be able to solve for any of those spots there. Any questions? Yeah. So this just demonstrates what we were talking about earlier. Remember that when we do have collisions, they do need to be sort of in the active spot to get things to stick and start reacting. Even though these guys collide through the carbon in the potassium, will not result in any type of product being made. And again, they also need to collide with the right amount of energy. The next thing we're going to talk about in this chapter is what is referred to as reaction mechanisms. Now, as you may be familiar with from previous class, when you talked about something like Hess's law. If you remember what Hess's law is, that's when you take a bunch of individual reactions and sort of put them together to make an overall reaction. And you can use each of the individual reactions energy values to figure out what the delta H for the overall reaction is. So not all reactions occur basically in a one-step process. Some reactions do take multiple steps along the way. So for example, again, it may be like A plus B makes C plus D, then like C plus D makes E plus F. And when we do add reactions or equations together, anything that's on opposite sides of the arrows can cancel or reduce. So in this case, C is on the left and C is on the right, so they will cancel each other out. D is on the left and D is on the right, so they will cancel each other out. It's kind of like the arrows an equal sign, like you subtract it off to the other side is the idea there. And then everybody on the left stays on the left, and everybody on the right stays on the right. And we get this overall reaction that occurs in a multiple step sort of situation. Now, reactions in general happen in multiple steps, and we sometimes refer to these steps as elementary steps or elementary reactions. And a sequence of sort of elementary steps is what is referred to as a reaction mechanism. And what a reaction mechanism is sort of a plausible way for a reaction to take place. It may not always happen that way, but it is a sort of logical way that this reaction may occur in multiple steps. And the reason that we think that these things happen this way is, for example, when we do this reaction here, where we take the NO plus the oxygen, make some NO2, during the reaction, N2O2 is detected, but it is not a reactant, it is not a product. So because it's detected along the way in the reaction, it is believed, obviously, that it has been made during the reaction, and it also must have been used up by the time the reaction was over, which is why we don't see it at the end of the reaction. So those type of things, as we'll talk about, are referred to as intermediates, and those are things that are made early on in the reaction and then kind of used up. So this is a plausible mechanism for how this reaction takes place. First, maybe a couple of NO guys come together to make N2O2, then that N2O2 and oxygen react to make two of the NO2s. Once again, here the N2O2 is our intermediate, as it is on both sides and completely cancels out, giving us our overall reaction that happens here. So there's some different types of mechanism problems we're going to talk about here, but one of a very common type of mechanism problem is this like a possibly good mechanism? Is this possibly how this reaction takes place? And you sort of have to prove if it is or not based on some information that's given to you. All right. So let's talk a little about some important parts of a reaction mechanism. First off, as I mentioned before, there are what are referred to as intermediates, and these are things that are made early on in the mechanism, but they do get 100% used up by the time the reaction is done, which means they do not appear in the overall reaction. So they get made early on, they get used up, they're no longer there when the reaction is done, and those are what are referred to as intermediates. So in our previous example there, the N2O2 was made early on in the first step, then it was completely consumed in the second step, and when we look at the overall reaction, it is not there, and that is a definition of an intermediate. We sometimes also talk about the molecularity of the reaction, and that's really the number of molecules that are reacting in an elementary step. There's unimolecular, which means it's just one molecule sort of reacting. There's bimolecular, which means there are two, and there's termolecular, which means there are three. Each of these have two guys reacting. So they're both bimolecular here in each of these elementary steps. They both have two reactants that are reacting in this case. Any questions on that? Now, when we look at a reaction mechanisms, there's a couple of things that we could do in a reaction mechanism that we typically don't do in a normal kinetics problem, but it helps us sort of achieve the overall end result of what we're looking for. And that is, we can actually, for each elementary step, and this is really the only place where you could do this in kinetics, you can use the coefficients in the elementary steps as the exponents. So you could write an actual completed rate law for each elementary step and using the coefficients. So for example, here in this step, the coefficient is 1. So we could write a rate law for this step where the rate is equal to k times a to the 1. These are both 1, right? Which means we could write a rate law for this bimolecular that the rate is equal to k times a to the first order and b to this first order. And for this one, this is essentially 2a, which means we could write the rate is equal to k times a and use the coefficient there as the exponent. So this is the only place where you can write a rate law for a reaction and use the coefficients as the orders is when you're doing reaction mechanisms. If it's not a reaction mechanism, you need to do what we did earlier, which is experimentally determine it using the table and the rate 2 over rate 1. Now, in order for a mechanism to be a good mechanism or a bad mechanism, which in oftentimes the case, that is sort of what you're trying to determine is this kind of good or bad, this mechanism. There's basically 2 things that you need to make sure of. The very first thing is when you add up all the individual steps in the mechanism, it needs to equal the reaction you're looking at. So if you happen to add up all the individual steps and it doesn't equal the same reaction that you're looking at, then it's the bad mechanism, obviously. So if you add up all the individual steps and it actually does equal the reaction you're looking at, it's good mechanism so far. The second thing that you need to make sure of or understand is there is something that is referred to as the rate determining step. And that is sometimes referred to as the RDS for rate determining step. The rate determining step is the slowest step in the mechanism. It is the one that really determines how fast, or I guess how slow, that reaction will take place. Hence the turtle. So it's kind of like in shopping, right? You get in the 10 items or less line, and you got somebody ahead of you who's got 400 items. So you're clearly not getting through that line until that person goes through there. So there's just always sort of a step in the mechanism that is the one that really determines how fast the overall reaction will take place. And that's what's referred to as the rate determining step. Now, the rate determining step will always match the experimentally found rate law. So in a lot of mechanism problems, they will straight out tell you the rate law was found experimentally to be this. And there should be a step that will match it identically to it. And that would be your rate determining step, and really the one that will determine the overall rate of that reaction. Now, the other way that you can determine which one is the rate determining step is a little bit more difficult. And in this case, what they will typically do is they will give you each of the individual steps, and next to them, they'll write fast and they'll write slow. So the one that is slow is the rate determining step. So sometimes they'll label each of the steps in there, and the one that is marked the slow step in the mechanism is usually your rate determining step. So those 2 things has to sort of happen for a mechanism to be good. Is all the steps need to add up to the reaction you're looking at. The rate determining step, once you determine that, the rate law for that should match the one that was found experimentally. Any questions on that there? All right. So rate law here was determined to be the rate is equal to k times NO2 squared. The reaction is believed to occur via 2 steps. what is the overall reaction? What is the intermediate? And what can you say about the relative rates of step 1 and step 2? So see what you come up with. Then we'll talk about it here. Okay, let's take a look and see on this problem. So first off, to get the overall reaction, we're basically just going to add these guys together. Now, in this case, NO3 will cancel on each side. We'll get rid of an NO2 there. That then means everybody on the left stays there. So that's NO2 plus CO goes to NO plus CO2. Any questions on that part there? The intermediates in this case is the NO3 only. NO2 is not an intermediate because why? Yeah, it does reduce, but it is still there at the end, right? Which means it cannot be an intermediate. Otherwise, it wouldn't be there at the end. So remember that the definition of an intermediate is something that gets made early on in the reaction mechanism, but does get used up by the time the reaction is done. So it really should not appear in the overall reaction. Any questions on that there? Okay, so now let's talk about sort of what we could get from this sort of mechanism here. We kind of erase all the stuff I scratched out. Now, because these are all elementary steps, and in each of these cases, they're bimolecular, there's two things reacting in each of these cases, we can use each of these elementary steps and actually write a rate law for each step. And we would do that by going to the first step, for example. And we would say that the rate is equal to the rate constant times NO2, and we would use the coefficient, which would be squared in this case. Again, here, if we didn't separate these, this would be the same as 2NO2, right? To basically putting them together. We could also write a rate law here for the second step, which is the rate is equal to K times NO3 times CO. First off, any questions on how I got those rate laws? Yeah. It's squared because although they separated it out here, there's basically two of them, right? So if we put it together and wrote the coefficient, it would be the 2. So that's why that would be squared. Yeah. Other question? Yeah. For step 2, it is always the reactants and it's the coefficient. So that is 1 for the coefficient here. So that's basically NO3 to the first order. And this is also 1, so that would be CO to the first order as well. So it kind of looks like 11 now, but first. Other questions on that? All right, so which one of these is the rate determining step? Which one's the slow step in the mechanism? It is the first one. So remember that the rate determining step, which is the slow step of the mechanism, should have a rate law that matches the one that was found experimentally. So this is the one that was found experimentally, and that matches perfectly the rate law that we see there on the first step. Yeah. So because those two match, something maybe show up better on the screen there. Because those two match there, that tells us that step number 1 here is the rate determining step or the slow step in this mechanism. So what we know about the relative rates of steps 1 and step 2 is step 1 should be slower, right, than step 2. Yeah. I would say in most cases, yes, there is sort of a mechanism problem where you would use the mechanism to figure out the rate law, but they would be labeled like fast or slow, and then you'll be able to determine which one is the rate determining step. Yeah. And that would be one where they would maybe ask, based on this mechanism, what would be the rate law that you would expect to find. Yeah. Other questions? Yeah. Yeah, so the rate determining steps should always have a rate law that matches like identical to the one that was found experimentally. So they should always match each other for that step. Yeah. Yeah. Because it has a rate law that matches the one that was found experimentally. So that would be how we know it. Other questions? And it happens to be the first step in this mechanism, but it won't always be this first step. So it's always the one where when you write that rate law or determine the rate law for that step, it should match perfectly to the one that's found experimentally. Yeah. Yeah. So once again, it may be given to you, and in most cases, it will be given to you. But as I mentioned back there, it may be a problem where you may use the mechanism to determine the rate law. And in that case, the steps would be labeled as fast or slow. So you would know the slow steps should be the same rate law that they would find experimentally. So I would say in a lot of cases it would be, but there is a sort of mechanism problem where it might not be. Other questions? Okay. So let's take a look at another type of mechanism problem and talk about how you approach these. So in this mechanism problem, we have several steps here, and we're looking to basically figure out, is this mechanism really kind of a good mechanism or bad mechanism? And this is the overall reaction that we're looking to try to determine. And in this case, this is really the experimental rate law that was found in this particular reaction. So we want to use we want to use this mechanism to help us determine, is it a good mechanism or bad mechanism? So remember, in this type of problem, there's really two things that we want to look at. We want to look at when we add up all these steps, do we get this reaction? So when we put all these guys together, do we get that reaction? So we'll start there to make sure. So if I add up all these steps here, I should have some stuff that crosses out. So let me see here. We have this guy that crosses out. We have that guy that crosses out. And I think that might be it. So everybody on the left-hand side will stay there. So on the left-hand side, we have 2 NO. We also have 2 hydrogens. And on the right-hand side, we have 2 waters. And we have a nitrogen. So that definitely checks out, right? If we put all these guys together. By the way, the intermediates here are what things? Yeah, so the intermediate is N2O and N2O2 in this case. So we actually have 2 different intermediates in this particular case. And again, both of those things canceled out and are not found in the overall reaction. So that meets basically, obviously, the definition of an intermediate. All right, so what we know is in order for this to be a good mechanism, all the steps has to add up to the reaction we're looking for, which it does. The second thing that it has to happen is the rate law for the rate determining step should match the one that was found experimentally, which is this one. So in this mechanism, which one is the rate determining step? It is a slow step. So that is a way that you determine it. This is our slow step here, which means this would be our rate determining step. That means that we could write the rate law for that step. And the rate law for that step would be, in this case, the rate is equal to K times H2 times N2O2 in this case, right? So that is the rate law that we want to see, does it match here? The answer is, does it match? The answer is, you really don't know, because we have one thing in that rate law, which is what? We have an intermediate in that rate law, right? So we have this intermediate in that rate law. which means we cannot really compare apples to apples, right? So in order for us to properly compare as to whether or not that step's rate law does match the experimentally found rate law, we kind of have to get rid of the intermediate. So to get rid of the intermediate, and this type of mechanism problem is kind of like in math, right? They have those proofs where you have a mechanism, you kind of have to prove that it's right by doing some math. And that's sort of the idea here. So we want to look in the rest of the mechanism to see where we can find that intermediate. And we do see it in the very first step, right? So we do see it in the very first step. Now that first step is actually a reversible reaction. And that's what the arrow is heading in both directions. So it's basically heading in both ways, this one. And that means that there is a forward reaction and also a reverse reaction that's going to take place, which means that you could actually write a rate law going in both directions. So you could write the rate law for the forward direction. So if we did that for step one, the rate law for the forward direction would be the rate is equal to K times NO squared. We could also write the rate law with it going in this direction. And when it's going in that direction, our products actually become our reactants, right? So we could write the, which would be K is N2O2. Any questions on that there? Now, when you have a reversible reaction, as we'll talk about in the next chapter as well, it will eventually reach what is known as chemical equilibrium. And what that means is not that you have equal amounts on both sides, but what it means is at some point, this reaction, the rate of the forward reaction, will equal the rate of the reverse reaction. So just as fast as it goes one way, it will come back the other way just as fast. And that's going to be helpful for me because that means in this particular example here, this number here and this number here, are they different numbers or the same number? They would be the same number if eventually it reaches equilibrium, right? So just as fast as it goes that way, it's coming back the other way. Although I don't really know what that number is, I do know that it's going to be the same number. That is important because that would then allow me to take the other part, right, and set them equal to each other. And that's what I could do in this case. I could set both of those things equal to each other. And that would give me K NO squared is equal to K N2O2. The goal here is to get rid of what thing in our original rate law up here? N2O2. So that's what we need to kind of solve for. So if I solve for this guy, I need to divide this K to the other side. And when I do that, I will end up with K times NO squared divided by K equals N2O2. Any questions on that? Now, using the first step in the mechanism, I have this guy, which is this guy, and I could take this entire thing and put it into that expression right there, right, in place of it, basically, kind of put all that stuff into there. So if I do that, I will now get an expression for that second step that the rate is equal to K times H2. And now again, I'm just going to put all that stuff in there. And that would give me K times NO squared divided by K. I could do a little cleaning up here. I have 3 Ks, right? And those Ks are the rate what? Rate constant, which means should they be same number or different number? Right, which means 2 of these will go away, right? Which means now I have the rate is equal to K times H2 times NO squared And now I have a rate law that has just the overall reaction guys in there. And now I could actually do a comparison. So earlier, pretty much everybody sitting here said, no, they do not match. I will re-ask that question. Does this one and this one match? They do. Now that we're comparing sort of apples to apples. So because the rate law for the slow step, now that we got it in the correct way or correct form, matches the one found experimentally, that means that this is a probable good mechanism. Yeah, it's possibly how this reaction could take place. That's in that case. Yeah. Question on that. So this is another type of mechanism problem where you kind of has to prove that it is or not, and you can do some substitution and use some of the math of the other things. What you have to do is have basically a rate law that you're comparing that is sort of apples to apples. You can't have intermediates in one and not in the other. Otherwise, as you saw earlier, it clearly looked like it didn't match, but once we got rid of the intermediate, we could see that it actually does match. Yeah. Question on that there. All right, well, I did one, so it feels like you should do one now. All right. Same idea here. Is this a good or bad mechanism, basically? Yeah. Here's the reaction. The 2 is kind of up here. So I'll move it down maybe. We'll put the 2 here. All right, so based on that reaction and that experimentally found mechanism or rate law, is this good or bad? And here, so remember, in order to evaluate whether or not this is sort of a good or bad mechanism or a plausible mechanism, we need really 2 things to occur. We first need to make sure that when we add up all the steps, we do get the reaction that we're looking at. And in this case, this is the reaction we're looking at. So when we add these together here, we're going to get rid of, it looks like the O there. And I think that's it. So that will then give us 203, and that goes to 1 and 2 is 302. So that part's all good. The second thing, in order for this to be a good mechanism, is that the experimentally found rate law, which is right here, does need to match the rate determining step. In this case, the rate determining step is which step? It is 2, as that is the slow step. So this would be our rate determining step. That means we want to start really with the rate law for our rate determining step, which is the rate is equal to K times O3 times O. And again, we want to compare those two, but we run into the same thing we had on the previous problem. We do have that sort of intermediate in there. So that's not going to allow us to make a true comparison. Again, much like the last problem, most of you would probably say it doesn't match at this point, right? But again, we're not really comparing apples to apples. So in this case, we want to look for another step that has the oxygen in it so we could do some substitution. It makes it really easy here since there's only 2 steps. It's got to be the first step to go to. This again is a reversible reaction, which will once again reach equilibrium. And we can again, for the first step, write 2 different rate laws, one for the forward direction, one for the reverse direction in this case. So the rate of the forward direction would be K times O3. Going in the opposite direction, our products become our reactants in this case. So the rate of the reverse reaction would be K times O2 times O. Once again, as we just talked about, this rate here and this rate here will be the same number, which means, again, we could set the other 2 things equal to each other. And if we do that, that will give us K times O3 equals K times O2 and O. At this point, we do want to solve for O, as that's what we want to really substitute out. So to solve for O, we're going to take all this guy and divide it to the other side, right? So when we do that, that will give us K times O3 divided by K times O2 will equal O. The concentration of O. Any questions on that so far? At this point, we now have O. That means that we could take this entire thing and basically substitute it in there, right? So we're going to substitute it into that rate law. That will give us the rate is equal to K, and I'm just going to directly write it the way it was. So that's going to be KO3 and KO2, right? Once again, we could do some cleaning up of this. Our K on top and bottom are going to cancel. That would then give us KO3 squared, right? Divided by O2. Now we have a rate law that we could compare to the one that was found experimentally. Do they match? The answer is they do match, yes. Because this is to the -1, which means it is 1 over O2, right? And then if you times that by the O3 squared up on top, you end up with the same one, yeah? So they actually do match here. And that means, once again, this is a good mechanism or a plausible mechanism. Now, in both of these cases, they both did match. They both ended up with a rate law to match, and they both obviously had the equations that added up to the overall reaction. Once again, if any of those things did not match, then it would be a bad mechanism. So it won't always be a good mechanism. It is possible it could be not really good or bad, plausible or not plausible type mechanism. So it won't always match. So just keep that in mind. Any questions on that? All right, we're laid up there for today. Let's talk about